This is part of the BocaPhysics Series on electromagnetism. Today's lecture is a continuation of the lecture on constructing the Green's function for the two-dimensional Laplace's equation, specifically applied to the system of a very long rectangular pipe of dimensions A and B. Now, in the prior lecture, we discussed how to construct the Green's function using direct expansions. Today, we're going to use contour integration. And if we're using contour integration, that means we're going to make use of the residue theorem. But before I can get to that, there's another theorem that I need to write down and I will also prove. So let me get to that straight away. So the theorem is that 1 over 2 pi I times the contour integral of the Green's function, the contour being taken such that it encloses all the poles of the Green's function, is equal to minus the delta function x minus x prime over sigma x prime. Now, the more general Sturm-Liouville equation, I should say, the Green's function counterpart to the homogeneous Sturm-Liouville equation. Is written like this. And remember, this is a function of x, this is a function of x, sigma is a function of x, lambda is a constant, and when we apply this to Laplace's equation, p is equal to 1, q is equal to 0, and sigma is equal to 1 as well. But I'm just leaving it more general here for this particular theorem. Now, in order to show this, I'm going to make use of the Eigenfunction expansion. So I'm going to switch the order of the summation sign and the integral sign. Move the minus sign out front. Okay, so if I make use of Cauchy's formula, this is just going to be equal to 2 pi I psi n x prime psi n of x. So therefore, the left-hand side is equal to minus summation n equals 1 to infinity psi n x prime psi n of x. Okay, so I need to show that this is equal to this. I'm going to go ahead and expand the delta function in terms of the eigenfunctions. So this is going to be n equals 1 to infinity, Cn, some constant coefficients, times psi n of x. Now, in order to extract the coefficient from the summation sign, I'm going to make use of the orthogonality of the functions psi n of x. So therefore, I'm going to multiply both sides through by psi n prime of x sigma x. So, and then integrate over the region of interest. I'm not particularly saying it's going to be from 0 to a, but just wherever your boundaries are. And then on the right-hand side, again, we can switch the order of the summation sign and the integral sign. And notice we do have to have a factor of sigma x in there because, again, we are applying this for the more general equation, not just Laplace's equation. So therefore, the left-hand side, we're going to wind up with psi n prime function of x prime and sigma x prime on the right-hand side of the board. This is just going to be the product of delta. That'll be delta n and prime, so that has the effect of picking out that one coefficient Cn prime. But again, these are just dummy coefficients, so you can leave off the primes there. So therefore, Cn is equal to psi n x prime sigma x prime. And therefore, your delta function is just equal to the summation n equals 1 to infinity, psi n of x prime, psi n of x, sigma x prime. And if I compare this expression with this one, I've shown that this integral is in fact equal to minus delta function of x minus x prime over sigma x prime. Okay? Well, this theorem is going to be useful when I show that the contour integral, in fact, is the correct solution. Okay? I'll leave this up there for a minute. The Green's function in 2 dimensions can be synthesized from the one-dimensional solutions by taking minus 1 over 2 pi I and doing a contour integral over the product of gx and gy. And this contour cx is constructed such that it only encloses the poles due to gx, but excludes the poles due to gy. And remember, gx and gy individually satisfy these two differential equations. Another way of writing this integral is minus 1 over 2 pi I, and this time taking a contour, we'll call it cy, constructed such that it excludes the poles due to gx, but encloses all the poles due to gy. And remember that lambda x plus lambda y is equal to 0. Now, the way I'm going to show that this solution is valid is by doing a direct substitution of this into the counterpart, Green's function counterpart for the two-dimensional Laplace's equation. Okay? And I'm going to make use of that theorem that we just proved. And remember, in this case, sigma is equal to 1. Okay, just going to want to show this first integral satisfies this equation. I'm not going to worry about the second one, so I'm going to go ahead and erase this. It's a good exercise, again, if you want to go ahead and show that or verify yourself this, in fact, is also a solution, but I'll erase it for now. So I'm going to insert this expression into my differential equations for the Green's function. And for brevity, I'm going to leave off the arguments. Also notice I added lambda x plus lambda y in there, which is fine because those sum up to be equal to 0. So this is minus 1 over 2 pi. Contour integral, we're integrating in the complex lambda x plane. Derivative, second partial derivative of g of x with respect to x plus lambda x gx times gy. And then I have my second differential equation, partial derivative of gy with respect to, second partial derivative of gy with respect to y plus lambda y gy and then gx outside. Well, I know what these two are. I can just look at my differential equations. I know this is equal to minus delta function x minus x prime, and then over here, this is equal to minus the delta function of y minus y prime. Okay. Now, when I integrate this first term here, this contour Cx doesn't enclose any of the poles of Gy. So therefore, this first term is just going to integrate to 0. My second term, however, is going to be equal to minus 1 over 2 pi. And I got minus minus, so that's going to give me a plus out. Right, and I've got delta y minus y prime. Contour integral of gx. So compare this expression with over the right-hand side of the board. I can see that this is just equal to minus delta x minus x prime times delta y minus y prime. So there you go, QED. We've shown that this contour integral does indeed satisfy this differential equation. So that is going to be how we will synthesize the two-dimensional Green's function from the one-dimensional Green's functions. Okay? Just leave it up there for a minute before we actually go ahead and write down the solutions. Okay? So the representations that I'm going to use for gx and gy are going to be based on this form. And g to the y is going to be okay. So g of x, basically this is the same as over here, other than I've added an x subscript to the lambdas, because of course we've got to distinguish between lambda x and lambda y. The y equation, it has identical form, it's just that we've replaced the x's by y's, and then also a's by b's, because remember this goes over from 0 to b, that goes from 0 to a. And let's see what else. Yeah, and square root of lambda y, as you'll recall, is equal to minus lambda x. Okay, so when I do this integral, and I'm going to write the lambda y's in terms of lambda x, so that means I'm just going to replace lambda y by minus lambda x. So again, this contour C of x encloses only those poles due to g of x, and it excludes the poles due to gy. So I'm going to need to calculate the residues. And just a reminder to use the residue theorem, if you are taking calculating a contour integral with some function f of z, that's equal to 2 pi I times the sum of all the residues that are enclosed by the contour. And to calculate the residue, well, there are a couple of forms. The first one is to take the limit as z goes to z naught, where z naught is a pole of the function f of z. Limit z goes to z naught, and that's of z minus z naught times the function f of z. Another useful form is equal to, let's suppose that your function f of z can be written some function g of z over some other function h of z. So the residue, that's going to be g evaluated at the pole z naught, and the derivative of the function h also evaluated at the pole z naught. Now, the only term that that we're going to have to worry about the poles from is this, or factor I should say, is sine square root of lambda x a. And let's see, I'm running out of room here. Let me just sketch it in briefly. I'll have to erase it right away. G of x has poles that lie along the real axis, real positive axis, and they're at n pi over a squared, okay? So those are the poles due to gx. Poles due to gy are actually going to be along the negative real axis, and that's going to be at minus n pi over b squared, okay? So basically choosing the contour such that it encloses these poles but excludes those. Now before I go ahead and tackle this entire integral, I'm just going to look at this one particular factor first of all. In other words, I'm going to figure out what the residue due to this factor is first by itself and then consider the whole integral. Okay, so basically if I look at the second form down here, g of z would just be equal to 1, and h of z would be equal to sine square root of lambda x times a. Therefore, the residue due to that factor by itself is just going to be equal to 1 all over cosine square root of lambda, put a, times a over 2 square root of lambda n. Remember, that's evaluated at the pole, which we'll call lambda n. You know, remember lambda n is in fact equal to n pi over a squared. Okay, so that's the residue if you were just calculating the integral of this by itself. Okay, so what I can do then is that I'm not just looking at the nth pole, but I'm looking at all the poles that are enclosed by the contour. So I'm going to have a summation n equals 1 to infinity, and in accordance with the residue theorem, that's going to, we're going to have a factor out in front of 2 pi I, summation n equals 1 to infinity, and then here we're going to replace all the lambda x's by lambda n's, okay? And then again, the residue due to this particular factor is going to result in 1 over a over 2 square root of lambda n cosine square root of lambda n a. And let's see, I'm just going to go ahead and erase this. Okay, so this is equal to minus 1 over 2 pi I, summation n equals 1 to infinity, sine square root of lambda n, x less than sine square root of lambda n, a minus x greater than, all over square root of lambda n, oops, I should be inside, square root sign, square root of lambda n, a over 2 square root of lambda n, cosine square root of lambda n, a, and we have sine minus our square root of minus lambda n, y less than, sine square root of minus lambda n, b minus y greater than, all over minus, or rather square minus square root of minus lambda n, sine of square root of minus lambda n times b. Okay, so I'm running out of room. I'm going to make some changes right here. Okay, so these 2 pi i's cancel each other out. And I'm going to replace square root of lambda n with n pi over a. So this. And by the way, this square root of lambda n cancels with that one. And this is going to give me cosine n pi. So all I did was to cancel out the one square root of lambda n and the other square root of lambda n. And I replaced a square root of lambda n by n pi over a. And of course we have an I there because of this minus sign. Okay? There's still a minus sign out front. This a will cancel with this one. The 2 will flip up into the numerator, and I'm going to pull the n pi over. And this cosine of n pi, I'll just leave that in the denominator. And I'm going to replace the sign of I that's in the argument by I cinch. But I'm going to have an additional I out here, I, and I down here, and I down here. And those all are going to cancel each other out. So let me read this off. We're almost there, not quite. Just got a little bit more manipulation to do. We still have a minus sign out front, summation n equals 1 to infinity. 2 over n pi, sine n pi over a, x less than, sine n pi over a minus x greater than, over cosine n pi. Then on this second factor, we've got sinh n pi over a times y less than, sinh n pi over a times b minus y greater than, all over sinh n pi b over a. Okay. So, I just want this expressed in terms of x and x prime. I'm going to get rid of the greater than and less than signs, but the first thing you do is to expand out this sign of n pi over a times a minus x greater than. So that's basically just equal to sine of n pi minus n pi over a x greater than. Okay? I'm going to use that trigonometric relation. This will be sine n pi cosine n pi over a x greater than minus cosine n pi sine n pi over a x greater than. Okay? So that's this factor right here. The first term in this, when I separate it out, it's going to be 0. Sine of n pi is always going to be 0 when n is an integer. The second term is going to give me cosine of n pi times sine n pi over a x greater than. Well, these cosine n pi's, if you got one in the numerator, one in the denominator, they both essentially are just equal to minus 1 to the n. So if you got product of minus 1 to the n and minus 1 to the n, that's just going to be 1. So therefore, this is going to be sine in pi over a x greater than. And you've got an additional minus sign, which cancels with this one out front. And one last change we need to make. When x is less than x prime, this is going to be x, this is going to be x prime. When x is greater than x prime, this is going to be x, and this is going to be x prime. So it doesn't matter which way I write it, x or x prime or x. That's just going to be summation n equals 1 to infinity, 2 over n pi sine n pi, x over a sine n pi x prime over a, sinh n pi over a y less than sinh n pi over a b minus y greater than, all over sinh n pi b over a. And this is exactly the same result when we did the direct expansion. And here we made use of the residue theorem by choosing a contour that only encloses the poles due to this g of x and excludes these poles. So let me just leave this up here for a minute before we move on to the final problem, okay? Now I'm not going to work it out and recall what the second representation was. Last time around we expanded in terms of eigenfunctions that were functions of y. Basically we just swapped the a's and the b's. Again, you could deform the contour c of x such that it goes into cy and enclose the poles due to this function instead of this one, but you're going to wind up with an expression that looks like the second representation we wrote down last time around, okay? Now, last but not least, I want to derive the Green's function when it was a double summation, okay? In order to do that, instead of using the form where I have the product of the two functions that one satisfies the boundary condition at x equals 0, the other satisfies the boundary condition at x equals a all over the Wronskian, I'm going to go ahead and use the eigenfunction expansion. And this time I'm going to use dummy index m for this particular expansion. So g of y, in this case, is equal to minus m equals 1 to infinity, 2 over b sine n pi y over b sine n pi y prime over b all over lambda minus n pi over b squared. So I'm going to plug this into my contour integral along with the same gx. Oh, and that should have a subscript y there. And because we are integrating over dx, I'm going to replace the lambda y by minus lambda x. And I've got a minus sign here, and I got those minus signs, so why don't we just get rid of those? Okay, so I'm going to apply the residue theorem once again to solve this. We already worked this out, that this term, if we were just looking at it by itself, would contribute this residue. So basically, we're just going to evaluate all the lambda x's at lambda n. And again, we're taking a contour that's such that it encloses all the poles due to this Green's function. And I'll pull both summation sides out front. Okay, so this is going to be equal to minus 1 over 2 pi times 2 pi I, which is from the residue theorem, so those are going to cancel out, get rid of those. And we have a double summation this time. Summation n equals 1 to infinity, summation m equals 1 to infinity. I've got an a over 2 in this denominator and 2 over b, so I'm going to go ahead and pull these out to the front. So this is going to give me a 4 over AB. And again, one last factor that we need to worry about. This is sine n pi over a times a minus x greater than. We just worked that out, this term is going to be 0, and that's going to be equal to minus cosine n pi sine n pi over a x greater than. So that minus sign cancels out with this one out in front, and the cosine and pi's cancel each other out as well. And we'll be left with sine n pi over a x greater than, but again, using the same reasoning as before, that's just the same thing as if we just mark one as x and the other one as x prime. So when we read it off, your solution is summation n equals 1 to infinity, m equals 1 to infinity, 4 over ab, sine n pi x over a, sine n pi x prime over a, sine n pi y over b, sine n pi y prime over b, all over n pi over a squared plus n pi over b squared. And that's your answer. Okay? So we worked out in the previous lecture 3 different representations. Here we just worked out 2.